Dawson, and this is my talk on lossless data compression. Cut the fluff and focus on the essence. So you may ask, what is lossless data compression? Well, first, let me just ask you guys the following question. Have any of you guys ever experienced this problem before? I used to run into this problem all the time with my old iPhone 6 with only 16 gigabytes of storage. People would always ask me, can you take my photo real quick? And I'd be like, well, let me quickly delete a few apps so I can actually, store the photo on my phone. And now this problem is actually entirely avoidable if I had just bought the iPhone with 32 gigabytes of storage, but it was significantly more expensive. And that's where the issue lies. Storage costs money. And I don't know about you guys, but I like to save money. So wouldn't it be nice if we could just reduce the size of all our photos and files and apps on our phone without losing any of the quality? That is precisely what lossless data compression is to reduce the memory size of apps, files, and messages without losing any information. So how does a computer actually do this? Well, first, let's just play a game of 20 questions. The game works by I'm thinking of one of the following items, each with a certain probability. And my question is for you guys is, how many yes/no questions do we need to ask on average to guess what I'm thinking of? When you may be thinking, well, why can't you just ask, MIT? Are you thinking of purple? Are you thinking of Yankees? Are you thinking of Red Sox? And so you'd be like, okay, well, on average, we need to ask 4 questions to think what you're thinking of. But we can actually do better than that by using the probabilities. So one informed solution to this problem we can do is first asking, are you thinking of MIT? If so, that means 1/4 of the time we get it in 1 question. If I say no, then you ask, is it the Yankees you're thinking of? If I say yes, that means 1/8 of the time we get it in 2 questions. If I say no, then you ask, is it purple? And if yes, that means 1/2 of the time we get it in 3 questions. If I say no, of course, I must be thinking of the Red Sox then, which means we get it 1/8 of the time in 3 questions. So if you combine all these, that means on average, we'll be asking 2.375 questions to guess what I'm thinking of. But can we do better than this? And we actually can do better than this by arranging the questions in the following manner. By first we ask, is it a color? If yes, that means, it's 1/2 of the time we get it in 1 question. If I say no, then you ask, is it a school? That means, we 1/4 of the time we get it in 2 questions. Then you ask, is it the Yankees? If so, that means 1/8 of the time we get it in 3 questions. And if no, then that means 1/8 of the time we get it in 3 questions. So now we actually got it down to, on average, we only need to ask 1.75 questions to guess what I'm thinking of. So I hope you guys start to see the intuition here is that we ask the questions with the greatest probability first and ask the questions with the least probability at the end. That way we ensure we use the least amount of questions possible to get the correct answer. And can we do better than this? We can't, because we made use of the probabilities. So how can we format our solution so it can be understood by computers? We do so using bits. Bits are simply logical states with one of 2 possible values. They're represented as 0s and 1s, and they mean true or false or yes or no. So it's perfect for our 20 questions game. So how do we actually represent our answers with these bits? We do so using prefix codes. Prefix codes basically operate by assigning each of our answers to a code that is a bit sequence. And a bit sequence is simply a series of 0s and 1s. So for example, 001 could be one possible bit sequence. And another important thing is that no code is the prefix of another code. And what do I mean by this? The reasoning behind prefix codes is, for example, say we represented our answers with the following prefix codes. So MIT is 00, purple is 01, Yankees is 0, and Red Sox is 1. You may ask, is this okay? That seems like a pretty valid solution to me, right? That represents all our answers with bit sequences. But then let me ask you the following question. What sequence of answers does the bit sequence 0001 represent? It could be any of the following because it's ambiguous. Yankees, its prefix code is 0, which is also the prefix of MIT and purple. So in a sequence, we couldn't actually know when Yankees ends and purple begins, or when Yankees ends and MIT begins. So that's why it's ambiguous. But by using prefix codes where it's not the prefix of any other code, we can ensure that there's no ambiguity and it's perfect for our problem. So the actual prefix codes for our answers could be as following. We represent purple with 1, MIT with 01, Yankees with 001, and Red Sox with 000. So basically it operates by just, if it's yes, we represent it with a 1. If it's no, we represent it with a 0. So the left in the tree is a 1, right in the tree is a 0. So how can we actually formalize this to be valid for any input, not just our 20 questions game? We do so using the Huffman Coding Algorithm. It first operates by creating a frequency table. We traverse the input file we're trying to reduce in size and create a frequency table where we map keys to their frequency in the file. So for example, if we had the file that only had the characters A, B, C, D, and E, and F, we would represent this with a frequency table as follows. And this is a 100-character file, by the way. So then what we do is we build a Huffman tree. And what a Huffman tree is, we first select 2 characters with the minimum frequency from the frequency table. Then we create a subtree where the root is the sum of those 2 frequencies. The left child is the minimum of the 2, and the right child is the other one. We add the root back to the table, and we repeat steps 1 and 2, or 1 through 3, until there's only 1 entry left in the table. So for example, if we had this table, we would say that A and B are the 2 minimum frequencies. So we would create the root node 14, and we would add it back to the table. Then we would see that the next 2 minimum frequencies are C and D, so we would create the root node 25 and add it back to the table. Then we would see that the next 2 minimum frequencies are actually the root node 14 and the character E, so we would create the root node 30 and add it back to the table. Then we would take the next 2 minimum frequencies, which would be the root nodes 25 and 30, and we would create the root node 55 and add it back to the table. So finally, then we would have the last 2 minimum frequencies are F and the root node 55, so we would create the root node 100. So our entire file is represented with this Huffman tree, and we're done because we only have 1 more entry left in the table. So you guys can see this is actually the same structure and idea of the 20 questions game, but instead of going from top to bottom, we're building the tree from bottom up. It's just easier to implement it as an algorithm, but it's the same intuition that we're applying the keys with the most frequency at the top and the keys with the least frequency at the bottom. So we can do the same process of assigning keys. So if we go left, we represent it as a 1. If we go right, we represent it as a 0. So this is a way of assigning prefix codes for our characters. So the memory size of this file, as a basis to represent it to, we could represent it with fixed length codes, which would require 300 bits to represent this. But if we do it with our variable length codes, like we just showed with the Huffman coding algorithm, we can actually represent this with only 224 bits, which is a 25.33% reduction in size. Pretty cool. So my final word on this is just to recap that lossless data compression means to reduce the size of a file without losing any information. The Huffman coding algorithm was basically assigning variable length codes to represent input characters, with the most frequent codes or most frequent characters getting the smallest codes and the least frequent characters getting the largest codes. So I just want to say thank you guys so much for listening to me. And if you guys have any questions, I'd be more than happy to answer them now.
All right, thank you so much, Cameron. Let's give a round of applause. If there are any questions, we do have a little time.